Yeah, so we've been talking about um, elementary equivalence. In general, on structures, we saw that isomorphism implies elementary equivalence. The converse is false, but on finite structures, um, these two are equivalent. And so if we want to talk about indefinability, we need some slightly different notion, uh, something where you can talk about some notion that distinguishes structures, right? So one notion that we will introduce, so a finer notion than elementary equivalence. And so that is the idea of M equivalence. And this says basically that for every formula alpha such that quantifier rank of alpha is less than or equal to M, let me take sentences for now. We'll worry about formulas later. So yeah, so the notion of this is rather than elementary equivalence, which just says that they satisfy all the same sentences. You are saying that you're partitioning them into equivalence classes, right? All those that satisfy formulas of quantifier rank 0, that's the quantifier free formulas, quantifier rank 1 formulas, and so on. What's the quantifier rank of a formula? Well, QR of an alpha is 0 if alpha is atomic. QR of negation alpha is the same as the quantifier rank of alpha. Quantifier rank of alpha or beta is maximum of quantifier rank of alpha, quantifier rank of beta, and quantifier rank of for all x alpha is. This is what you would expect, quantifier depth or quantifier rank. Yeah. So disjunction, you take the maximum. That's also clear, right? That if I were to look at the quantifier depth, you want to take the maximum. And so this is the refined notion now. And corresponding to that, there is a notion of M isomorphism as well, a partial isomorphism notion that was introduced by Freyze. I'm going to skip that. I'm only going to talk about the notion that was defined by Ehrenfreud, which is game theoretic and more intuitive. So we'll work only with that. Of course, these are called Ehrenfreud-Freyze games because to say that they are all equivalent. And the notion of partial isomorphism is also very natural. It's just that I don't want to go into it. We have only so much time to look at topics. So I'll define only this notion. So let's call this by this notation. And this says that A is M equivalent to B if player 2 has a winning strategy in the M round game. Let's denote it as so we have a two-player game associated with a pair of structures, and when you look at the M round game, in that player 2 has a winning strategy. So what's the game? I introduced this, and these are called Ehrenfreud games, and I introduced that last time on linear orders, but in general on structures we can define it. So the way it goes, so in general you are not given just A and B because you want to work not with sentences but with formulas. So there will be some assignment for free variables. There are some k variables, you will have k elements already assigned to it when you look at it. So normally the thing is defined with not just structures with some elements, we call some sequence of elements. So the length of, yeah, some k tuple of elements from A and a k tuple of elements from B, that's already given. Now this is a two-player game. To play a game of perfect information in the jargon, and so we'll just prosaically call them 1 and 2. They're usually called by colorful names, like one is called spoiler and 2 is called duplicator. Basically, duplicator is trying to say that they are actually M isomorphic. Spoiler says they are not. So that is their goals, right? So player 1 is called spoiler because he wants to spoil the symmetry between the two structures, and 2 is called duplicator because she wants to show that they are in fact symmetric. They satisfy the same formulas. And the game proceeds in rounds. So a round consists of a move by player 1 and then a response by 2. Total of m rounds. Of course, you can have the version of the game. Siddharth, you didn't miss anything because I'm just going over what we were talking about last time. Yeah, I was doing it for linear orders, but in general, this is over any structures. Yeah, so we are only looking at finite structures now, so that also should be clear. So move by 1 is select one of the two structures and an element from it. So player 1 says, okay, I pick the structure A and this particular element, little a in it. And the response by 2 is an element in the other structure, right? So this length is always preserved. If you start with a k tuple, right, a k tuple of A's and k tuple of B's, after one round you will have a k plus 1 tuple of A's and k plus 1 tuple of B's. Is this clear? And in general, you could choose one of the already existing elements, a new element, it's up to you. And it goes on, right? And player 2 wins. So this goes on till 2 wins if both structures, so basically the A restricted to A bar and B restricted to B bar satisfy the same atomic formulas, right? And so this is the deal. So for all your variables, you have got your interpretations from these. So now you restrict yourself to these elements. So that is the idea of partial isomorphism. So yeah, I'm not defining that, but they satisfy the same atomic formulas. So that means what? When I plug it in for whatever relations, right? And by the way, I mentioned this last time, I'm only working with a relational vocabulary, no function symbols. And for simplicity, for our discussion, let's throw away the constant symbols also. Yeah. So there are only relations. It's what is called the pure vocabulary. So you have formulas with variables, no constants, no function. The only terms are variables, right? So you just have to assign variables, elements of the domain, and you only say that the relations are satisfied. Equality, of course, exists, right? You have equality, inequality. This is it. This is the game. And of course, if player 2 loses, player 1 wins, right? 1 wins otherwise. So the deal is that you start with a sentence, right? The sentence has quantifier rank m. every move reduces the quantifier rank, right? And in the process, you keep assigning elements to variables. Think of it as player 1 takes an existential quantifier and picks an element, right? Look at what is the objective of player 1. Player 1 is a spoiler, right? So if player 1 is winning, it is by showing that there is a sentence, right? There is a formula, if you like, that is true in one structure but not in the other. Now that's a quantified formula, right? So it's one of them is that there exists and the other is a for all, right? So structure A satisfies there exists X alpha, and structure B satisfies for all X not alpha. I mean, if it's a distinguishing thing, it should be something of that kind, right? Because we are talking about some quantifier rank M in particular. Now let's look at M greater than 0, right? So player 1 looks at one of the two. One of them satisfies there exists and the other one satisfies for all, right? With a negation. He picks the existential one. That's the idea of the picking the structure. And then the witness will give some element. Now, this player 2 is the for all player here, right? So picks some element, any one of the elements should be okay. You keep going like this, and at the end, all the quantifiers are stripped and you have only atomic formulas. And the atomic formulas are already evaluated for you. That is a deal, right? And now you want to check that all the relations are satisfied. A particular relation is satisfied over one structure if and only if it's satisfied in B. This is the idea of, so basically that if player 2 had a winning strategy, right, that means what? That no matter what player 1 picks, right, I always have a correct response. That's really what this is saying. Yeah? I mean, intuitive idea should be clear. Yeah? So, of course, we'll define all the notions, but what is a winning strategy, etc., etc. But this is the definition of the game itself. The game itself is very simple. It's and the way I have defined it, it's the number of rounds is fixed. Now you can have, of course, a game where the number of rounds is not fixed, and it can go on forever, so that you can evaluate this over not just finite structures, over infinite structures, whatever, and the theorem actually holds. But our interest is in particular in the finite case, because as I said, in the finite case, you want to distinguish, we want something finer classification than isomorphism and elementary equivalence, so we are looking at it for that purpose. So before we get to the formal definitions, let's take a little example. Last time I took the example of linear orders and finite linear orders, and showing that, so what is the idea? That if A and B are finite linear orders, right? So both of length greater than 2 power n, then there is no formula of quantifier rank n can actually distinguish linear orders which are longer than 2 power n. And it's a very nice proof where you can show that player 2 has a winning strategy, right? The idea being that player 2, so whatever be the distances, right, intervals, if you think of it as intervals, the linear order, finite linear order, think of it as some interval of natural numbers, right, some segment of natural numbers. And the idea is that whatever distance between AI and AJ is there on one structure, player 2 repeats exactly the same distance, and unless both are greater than 2 to the n minus m, where you're n minus r, where you're playing the rth round. So that is the invariant that you maintain, and it works very nicely. You can check that, you can always do that. The example I want to take now is, here is two graphs. So one is G and the other is H. So G is two triangles. So let me call it 1, 2, 3, 4, 5, 6. And here I have 1, 2, 3, 4, 5, 6. Let's call it 1 prime, 2 prime, 3 prime, 4 prime. A hexagon. Yeah. The claim is that player 2 has a winning strategy in the EF game, the 2-round EF game over G and H. And this should be easy to see. Why? Well, it's a 2-round game. No matter what player 1 picks, if player 1 picks an element here, player 2 responds with 1 prime, right? And then let's say player 1 switches to the structure and picks 2 prime, you pick 2. If player 1 picks something apart like 3 prime, right, you go over to there is 4, for instance. Yeah. So you can put in a 2-round game for 2 elements, whatever choice that player 1 makes, you can give a corresponding answer. But of course, it's easy to see that the moment you go to 3-round game, or of course higher, in 3 rounds player 1 wins. Why? Because player 1 will pick a triangle, right? And there is no triangle in H. No way can you get the same atomic formula is true. Yeah. So in the language of graphs, it's easy to see that the moment you have 3 rounds, you have a winning strategy. So the number of rounds matters, and this is exactly the idea that, and of course, what is the quantifier rank formula of quantifier rank 3 that distinguishes the two structures? It's easy to see. There exists x1, there exists x2, there exists x3, E of x1, x2, and E of x2, x3, and E of and that's a distinguishing sentence of quantifier rank 3. But what is very nice is that we are also saying that no formula of quantifier rank 2 can actually distinguish the two structures. So this is precisely the kind of expressive power that we want to discuss in this. Because elementary equivalence is too coarse and it describes structures up to isomorphism, and so we want to have finer classification. And this is the beginning of descriptive complexity theory, where you are describing structures in logic, and you are actually trying to see what kind of resources you need, what are the logical resources you need, right? And here the logical resource that we are working with is quantifier rank, and of course the descriptive complexity theory looks at many more things. You can look at number of variables, number of free variables, lot more fun. I mean, and I said relational vocabulary, how many, what, so it's a whole new topic. But quantifier rank is the simplest thing, and EF games show you a very nice way of looking at this. Any questions on the example? Is it clear? Okay. I don't know what has happened to Siddharth. He probably lost connection. Already he lost twice. I don't know whether. Yeah, Ananya is not well, but Siddharth said he's going to be here. Okay. What's a strategy? A strategy is I'm not going to write it as a map. If you write it as a map, you have to consider moves. What's a move? A move is a pair, a structure and an element, right? And a response for player. So a strategy will then be a map from sequences of rounds to a move. Strategy for player 2 would be a map from sequences which are sequences of rounds and a move to a move. And but finally, after all that, you will just say all these things formally. Right now, I am not interested in that. You can. So, strategy for player 1, importantly, will tell you, given any configuration of the, what's the configuration of the game? Configuration is something of this form. Yeah. So, that's one configuration. And then you might have right. So, player 1 makes moves in configurations of this kind, where the sequence of elements are of exactly the same length, initially null, right? And player 2 moves. So, these are player 1, 2, and this is where player 2 moves. And of course, a legal move will tell you that you have to pick from the other structure, right? Whichever is the. So, in this case, you have to pick an element from the B structure. Here, you have to pick from the A structure. So strategy is basically a map which tells you whenever it's player 1's turn to move, what should you do? It should pick a structure and a move in it, right? An element in it. And strategy for player 2, let me use tau. Is a map from player 2 positions, so sequences of rounds ending in a position of this kind, and what it's a map to an element in the other structure. That's all. So these are all possible maps that you can consider. Right? Given any structure, pair of structures A and B, you have a whole class of functions, sigmas and taus. Right? Now, note that given a pair, sigma tau, it results in a unique play, and hence the moment I fix a pair of strategies, one for player 1 and one for player 2, it results in a unique play. What's a play? It's a sequence of rounds. Here you are allowed only m rounds, so you go for m, right? And why? Why do you get a unique play? Well, when you start, player 1 has to start. Sigma will tell you what to do. Remember that sigma is a map for player 1 from all sets, so it includes the null sequence as well, right? So it will tell you a move for player 1. Well, that will extend it by 1, and now it's a player 2 position. Tau will tell you what to do. What is the response? So that will give you 1 round. Now you have again got even length, same length sequences. So player 1 makes a move. So sigma will tell you apply sigma to the 1 round sequence, and it will tell you what to do. Apply now tau to it, you will get a 2 round sequence. Keep doing this. At the end of m rounds, somebody wins. Either all the atomic formulas are preserved, in which case player 2 wins, or there is some distinguishing atomic formula, in which case player 1 wins. So every pair of strategies always results in a unique outcome for one of the two players. And this is the basis of game theory. This is what is called normal form representations. In the case of two players, so you can write it as a matrix. So sigma, let's say, are all the rows and tau are all the columns, and the entry you put in is, it's a, for instance, in the case of 1 for player 1, win for player 1, you put a 1. If it's a loss for player 1, you put a -1. So you will have -1, 1. Entries will all look like that. Every combination sigma tau will, we're not going to do any of that. I'm only telling you that you can do. So this is sigmas and these are the taus, and the entry. This is an example of what you call a zero-sum game, because the payoffs are 0. So this is typically how game theory is done. We don't need any of that because we are doing something. We are using it as simply notation for saying certain things. I'm not going to go more into that. Now, I say that sigma is a winning strategy, and that's the only definition I need. For player 1, if for all tau of 2 and similarly tau is a winning strategy for player 2 if for all strategy sigmas of 1 sigma tau is a win for tau 2. So this is the idea of a notion of a winning strategy. It's a map that tells me what to do such that if I follow that advice, it doesn't matter what the opponent is doing. For every possible strategy that the opponent is using, that means whatever move is made by the opponent, right? Because it quantifies over all strategies, therefore it quantifies over all moves, the result is always a win for me, right? So such a function. Now, there is a fundamental theorem going back all the way to Zermelo in 1913, which tells that you take any finite game, if the set of strategies is finite for both the players, then either of the two players has a winning strategy. Of course, both cannot have a winning strategy, right? Suppose player 1 has a winning strategy sigma and tau is a winning strategy for player 2, you are in trouble because the unique play that you will get has to be a one for only one of them, right? Both cannot win. So given any game, it's not possible for both players to have winning strategies, but it's very reasonable to ask, does any one of them have a winning strategy at all, right? And maybe it's that neither of them has a winning strategy. But as I said, there is a theorem which says that no problem, as long as you're talking about finite games of perfect information, two-player games of finite games of perfect information, as long as the depth of the game is finite, right? In this case it's an m-round game, so the depth of the game is finite. One of the players has a winning strategy. That's also very easy to prove, but we don't need that. This basically says that my M equivalence is well defined, right? The Ehrenfreud equivalence that I defined on two structures, saying that, so in particular now we'll be talking about A bar, this structure with this evaluation satisfying alpha if and only if, where this has some m free variables, x1 to xm, and this is of length m, with the idea that x1 is assigned a1, x2 is assigned a2, and so on, right? Rather than writing it as pi, I am just writing it as the sequence notation. Yeah, this is just a notation for saying that. So alpha x1 to xm, and here you have a, with the understanding that xi is mapped to a. Yeah, this is just notation for talking about that. And in the case of the m, if we start with the quantifier rank m sentence, when you arrive at after m rounds, you're going to have all the quantifiers are interpreted. Remember, you started with the sentence, no free variables, right? So at the end, the only free variables are going to be those which are already assigned here, and you can check this. So this is the deal. Any questions? Yeah. So it should be important to understand the difference between strategies and winning strategies, right? Strategies can be anything, right? You can, I mean, nothing stops you from playing a completely bizarre strategy, right? So I mean, in a game, you are allowed to always, order your cards in whatever way you like, and I always play the leftmost. I mean, if you don't care about winning or losing, you can play whatever you want, right? So strategies are simply arbitrary maps. Anything that's legal is okay, right? So that's all. Like for instance, player 2 has, I mean, by legality, I always have to pick a move in the other structure. You have picked one in B, then I have to pick one in A. That's all, right? What you play is up to you, right? Winning strategy is something else. Winning strategy says that it's a map such that no, it quantifies over all strategies of the opponent, right? So that's the only thing to keep in mind. And now so this is basically the statement, and the theorem, the proof of the theorem is really straightforward. And so, yeah, so the theorem, try this now. Yeah, so what is the, yeah, I'll write it like this. Yeah. Now, let's assume that suppose this is actually done by induction on M. So and that's very reasonable also, right? By induction on M. And the base case is quite clear, right? By definition, right? In the 0 round game, yeah, no moves are made at all. In the 0 round game, player 2 wins if and only if quantifier rank 0 formulas are all atomic formulas, right? All Boolean formulas, or if and only if all the atomic formulas are satisfied. And if all atomic formulas are satisfied, negation, disjunction also follow. Boolean combinations also follow by routine induction, right? So it should be clear that it follows straightforwardly by, right? If two structures satisfy the same atomic formulas, of course they satisfy Boolean combinations of atomic formulas as well, right? So that's clear. So for the induction step, suppose A bar is m plus 1 distinguished by B bar, right? So there is so therefore there is some distinguishing sentence phi of quantifier rank m plus 1. Okay. Now, if phi is of the form not C, right? Yeah. It's a distinguishing sentence means what? It's satisfied here, but it's false here. In the case of not, it's the other way, right? If not C is a distinguishing sentence, so is C, right? So I don't have to worry about that. If phi is of the form psi 1 and psi 2, then one of them is a distinguishing sentence. right? So it suffices to consider phi of the form there exists x c, or for all x the other way, right? Where quantifier rank of c is less than or equal to m. Yeah, yeah, here of quantifier rank less than or equal to m plus 1. So we might as well assume equal to m plus 1 here, because for the induction, and this is of quantifier rank m. Yeah. So now, again, without loss of generality, let's assume that so it satisfies. Yeah, that's the distinguishing formula. And well, then for some element a, which is the domain of the structure, a bar a satisfies p, right? And x is free here. And by the way, I'll assume that when we start, we consider sentences only which are standardized apart. You remember the sentence, the terminology that I said, so that you don't mess with you have there exists x alpha coming, and inside which there is another there exists x, and so on, right? Rewrite all the bound variables so that there is no clash of variables, all this stuff I assume. And also you don't have there exists x alpha where x doesn't occur at all. So don't, so that we can maintain lengths carefully, right? So that, you can always put x equals x if you want inside, so that, right, the damn thing actually occurs free, right? So otherwise you can get into this, some silly pathological problems, and, which are simply meant to harass students and in exams and stuff, but, not really relevant for proofs. Yeah. So clearly there is some A such that this is true. And we in fact know that, on the other hand, for every B in the domain of the other structure does not satisfy C, right? So indeed, C is a distinguishing sentence for this pair. Yeah, because that's really what it means. This for every B. Yeah. And now, therefore, so now I can apply the induction hypothesis, right? So I know that player 1 has a winning strategy in the I want to show that, what is it that I need to prove? I need to prove that I started with these two being m plus 1 inequivalent, right? So I have to show that player 1 has a winning strategy in the m plus 1 round game with A bar and B bar, right? So now the claim is that I can show, now by induction hypothesis, player 1 has a winning strategy in the m round game with A bar A, B bar B, right? Now, since, so and therefore now we have got a winning strategy for, and this is indeed the winning strategy because this is true for every B, right? It's clear that player 1 takes A here and whatever is the winning strategy here, let's call that sigma, right? So sigma prime, let's consider sigma prime, which is picking A and this A and this element here, followed by sigma, and then play sigma, right? This is a winning strategy for player 1 in yeah, this is the idea, right? So for player 1, what is the winning strategy? First pick the structure A here and the particular element A here. After that, imitate whatever is the winning strategy that is available in the inductively given structure. And that it's a winning, this is a strategy clearly, that it's a winning strategy comes from the fact that this is true for every B, right? And so this is a, that's why I said it's simply a restatement of that. So one direction is very easy, other direction is also not difficult. There is a slightly subtle remark that we have to make, that's all. So is this direction clear? So if there is a distinguishing sentence, then player 1 has a winning strategy. Yeah, that's what we want to. Now, on the other hand, suppose that we want to argue that player 2 has a winning strategy, right? If in the these two are m plus 1 equivalent, they satisfy the same formulas, then it's indeed the case that player 2 has a winning strategy. Now for this, so the simplest way to argue is that, maybe I can go the other way as well. Yeah. Okay. Yeah. So firstly observe that so fix some k, finitely many formulas in k variables up to logical equivalence actually true in a structure. Once you have a, remember we have a finite vocabulary, finite relational vocabulary. That's what, remember the language that we are working with is a relational vocabulary, and you have only finitely many relations. Now, and I consider only formulas with k variables, right? Remember that we are going to we are working with the m round game, right? And each time we are stripping off one variable. That's the idea. So the number of variables is fixed for us. So how will these formulas look? These are called Hentica formulas. So basically, I can talk about, say, fix any structure C and some sequence of elements C bar. where is n, and I am looking at formulas over n variables, right? So now we are looking at n variable form, n free variable formulas. So let me call it phi 0 of C bar of the structure, this model really, right? We now have a structure and an assignment for the n variables, right? So my point is that you can define that finite model by formulas. Formulas of quantifier rank, whatever is the quantifier rank that we want, right? Some m. So let's see how to define that. Yeah. So there are two things here. One is k, the number of variables, and the other is m, which is the quantifier rank. Yeah. So I write these as and over alpha atomic satisfies alpha x1 to xk and over alpha atomic If you remember, when I talked about describing a graph up to isomorphism, this was the idea, right? Wherever an edge is present, suppose the graph is a k element, k vertex graph, right? Your edge relation will say there is an edge between Vi and Vj. There is no edge between Vk and Vl, right? So wherever an edge is present, you write E Vi Vj. Wherever an edge is absent, you write not Vi, not E Vk Vl. So using your atomic formulas, you can completely describe the basic structure. This is the idea. So these are atomic formulas, and this is the idea. So this, even though the structure, there are infinitely many, even if this structure is infinite, even if you have infinitely many elements, there is no problem, right? Because I am only looking at variables, right? I'm looking at atomic formulas, and this is the pure vocabulary. I'm looking at something with no constants. We can extend this with constants also, but it's just more painful and more detailed. But there is no problem with that. I just have to write x1 equals x2, x5, not equals x4, whatever, and write out all these things. I think Vinod was that day asking the question about, should I write this or not? Because, like, for instance, in the case of simple graphs, you don't want self loops and so on, right? So you have to make sure that if I write there exists x1 to xn for some m elements, I have to make sure that xi is not equal to xj and so on, right? So you have equality, and you have in the case of the graph, you have the edge relation, and I can write this. And remember, this was how I constructed the distinguishing sentence as well, right? There exists x1, there exists x2, there exists x3, e x1 x2, and e x2 x3, and e x3 x1 in the case of the triangle. In the case of the hexagon, I would be writing all these e x1 x2, e x2 x3, not e x1 x3, etc., right? So this is all the quantifier free formulas. These are the quantifier rank 0 formulas. What will be the quantifier rank m plus 1 formulas describing CC? Well, this will be there exists x and over, and over alpha let me write A if you like. Yeah, I have extended this sequence by an element A. This is n plus 1. There exists xn plus 1 alpha yeah. Yeah. So whenever I can extend by one element and then this formula is satisfied, I have to just write alpha here if you like, and over A, and yeah. So I take every such formula, right, for every extension that it satisfies alpha. Now with an alpha with n plus 1 free variables, then I put in there exists x1 xn plus 1, and where alpha xn to xn wait, sorry, I have to write, yeah, I think this is what I have to write, just check. Sorry. Yeah. Yeah, so let me write it properly, sorry. So, and over, let me just write A in this thing, there exists x n plus 1 and phi m I've written C bar, sorry. And over and for all xn plus 1 or over A belonging to A, same thing, phi m yeah. So let me just tell you what I am saying. Quantifier rank m plus 1 formulas, what is the description? It says if you take any of the formulas with n free variables, I can put an existential quantifier and then talk about this for every extension of this is not C but A but C. Yeah. Belonging to C. Again, now if the structure were infinite, this looks like an infinite conjunction, right? But the point is that there are only finitely many formulas up to logical equivalence, right? So even though if you take over all the elements, the number of formulas that you can have syntactically is only finitely many, and that's what saves you, right? And so this is says, so for every element for which there is a witness there, you write there exists x and put it in. Same thing again, right? If you have a particular vertex, right, that you have got, which now you've already talked about the formula on triples, maybe on triangles, on some three variables, you have defined some relations. Now you consider a fourth element, right? And that fourth element is being related to the three elements in various ways. That's what is going on here, right? You put it there exists x for each of them and write. And this is now for all xn plus 1, one of the elements should actually satisfy it, right? One of the extensions by these things will satisfy it. And it's easy to convince yourself that this, so I can define for, you give me any structure, right? Now I can look at all formulas of quantifier rank, all sentences of quantifier rank if you like, right, can be completely described. All the formulas of quantifier ranks true in that structure can be written down. So this is basically, and this is really what we need for the proof here, right? So if two structures are m plus 1 equivalent, right, I can go for the actual formula of quantifier rank that completely describes that structure, right? So, and this is really it, right? So, inductively for quantifier rank M, now your friend player 2 has a winning strategy. Now, when I look at the describing formula for rank M plus 1, it tells you exactly what player 2 should do, right? Because no matter what you pick, right? And this is the main idea. If they satisfy the same sentences, right? If there exists X is true in one, then there exists true in the other, right? So whichever one you pick, there is a witness, there is a corresponding witness in the other one. This simply comes through by semantics, and then so for each choice of B, you have a phi B, if you like, right? You have, for every choice you will get, and now there is a formula that completely describes the quantifier rank M, and that gives you inductively a winning strategy for player 2, right? So this particular formula, if you unroll it, right, it gives a winning strategy for player 2 at every step, such that when you come to 0, it will give exactly the atomic formulas that are true, right? So player 2 wins. In fact, this winning condition can be strengthened to actually say that not player 2 wins at the last step, but player 2 wins if at every step the atomic formulas are preserved. It doesn't really matter. It will come out to be the same thing, right? Because finally when you take the restriction over these structures, you have to anyway consider all the intermediate steps as well, right? Okay, so that's basically it. And so the EF theorem is one very nice way of characterizing finer equivalence, and that already gives you lots of Poisson. Now you can, and I've already hinted at what was the graph that we looked at. One was two triangles and the other was the hexagon. Yeah, that these two graphs, right, cannot be distinguished by quantifier rank 2. So this already tells me what is a distinguishing property between these two graphs. Connectivity, clearly, right? H is connected, G is not connected. So this already tells me that connectivity is not F4 definable, because if it were definable by a sentence, it will have some quantifier rank, right? Say n. Now I consider two graphs sufficiently large, and typically 2 power n will do, right? Take an exponentially sized cycle and the other one which is two copies of the same, and then we can play the EF game to show that player 2 has a winning strategy in the end round game, and therefore there is no formula of quantifier rank n, but you assume that there was one, and that's a contradiction. This is just to give an example. But it's really fun to try to construct. So you can show that Hamiltonicity is not definable. Lots of and why graphs, right? You can look at arbitrary relational structures and prove very interesting results over finite structures. So what I said was that over arbitrary structures, compactness is the real tool that we have got to show indefinability. Like we saw examples of that, and elementary equivalence is another very nice example where we showed that the rationals, the theory of order over rationals and the theory of order over reals is not F4 distinguishable, right? So if I take the first order theory of order, it cannot distinguish between, it can distinguish between integers and rationals, but not between rationals and reals, right? And so that's just showing elementary equivalence, back and forth technique. Compactness is used, for instance, to show that piano arithmetic cannot distinguish between the number line and many copies of number line, one sitting on top of the other, right? And compactness is the tool, but unfortunately that's not available when you restrict yourself to finite models. For finite models, EF games is the tool. But there is also this technique of reductions, right? It's a pity that some others are really missing this important point. Maybe I'll tell them separately. But let me just show that now that we know that, okay, so last time what I talked about. So you can use EF games to show that over two linear orders, right? Formulas of quantifier rank n cannot distinguish between linear orders which are. This tells me immediately 1, parity is not definable in the language of order. Why? Well, consider two structures. Yeah. Suppose you have the property of evenness, right? Even length. Yeah. If there was a sentence that is true over linear orders if and only if they were of even length, right? Well, that will be true over A and B, but this is length is odd and you have a problem, right? So whichever odd or even, whichever way you like. Now, and this argument, like I said, the EF game that we followed, the winning strategy for player 2 is very generic, right? So you can use it for parity, you know, length is 0 mod k. For any k you have similar kind of arguments. The constants, whether you work with 2 power n or 3 power n or what is the sort of thing that you work with is something that you have to be carefully work out, right? In general that will always be the case, but yeah. So the property of so this is the applications that I was talking about. It's not only the application of the EF theorem. My point is that once you have some particular property not definable, you can do a lot of reductions and show many other properties are not definable as well, right? And that technology is extremely important, right? Like I said, it's a pity that Ananya Siddharth are all missing this, but hopefully I'll take them through it another time. It's very important for, I mean, pretty much all complexity theory is about doing reduction, so you better, they have to get used to this way of thinking. So the property of being an even member, say, in a linear order, even position, is not definable. This says even length, right? First, from the description that we had, we can show that the length of the linear order being even is not definable. Now I am saying consider a property that is true only at the even positions, right? So formula with one free variable, right? P of x, right? Such that if you look at all the elements of the linear order on which it is P is true, they are all even positions, right? That's also not definable. Why? That should be easy to see. Suppose it were, right? Then I can write, so let's say phi x. Phi x says x is true at even positions, right? Then consider there exists x phi x, and for all y less than or equal to x, right? Defines even length, right? Or odd length, one of the two, I don't care, right? I've forgotten which. Yeah. Yeah, it depends on whether you count from 0 or 1. Huh? Yeah, okay. In any case, yeah. Yeah, if the that's the length of the string, length of the linear order, right? And this is the maximum element. Yeah. So yeah, so that's a trivial example. Much better is this. Connectivity is not definable in the language of graphs by reduction to what we just did, by parity. How do you show that? Well, consider this picture. 1, 2, 3, 4, 5, 6. So I connect. No, sorry, I screwed up the connection. 1, 2, 3, 4, 5, 6. So 1 connects to 3, 3 to 5. Second last element connects to first. Yeah. 7. 1 to 3, 3 to 5. Last connects to second. Second connects to first. Yeah. So what I write is that less than is a linear order. And then I write that y is the successor of x if and only if y is equal to x plus 1 or y is second last and x is first, or y is last and x is second, right? Over linear orders, this is all happily FO definable, right? That less than is a linear order, I can write as a first order formula. Now, this formula is true in the linear order if and only if the associated graph that I have got is connected. Yeah. So this is the classic way of doing reductions. Yeah. So
John, is it y is equal to x plus 2 or x plus
x plus 2, sorry. Yeah. Yes. Yeah. So what I am doing is you take the given graph. So suppose connected, so in general you take the sentence phi in the language of graphs, and wherever exy comes, I replace it by less than xy, and then consider the sentence where I append with this this particular extra formula. And the claim is that the original formula is true in the over a connected graph. If and only if the corresponding sentence that I have come up with is true over the linear order. But clearly this sentence, as we can see by this my little demonstration, is that it describes parity very nicely. I mean, this is a classic trick. I think I've seen it in Immerman or one of the books. Yeah, I mean, it's used in many places, and almost any complexity book would have this connection between linear orders and connected graphs, right? So the graph is connected if and only if this thing is of what odd length is it? Yeah, it's the number of elements is odd. Yeah. So by reducing parity, you can now show connectedness is, and once you show connectedness is not definable in finite graph, and this is really important. Remember, I did a proof earlier to show that connectedness is not definable in arbitrary graphs using compactness, right? Using compactness you can show, but that is true for finite as well as infinite graphs. That argument of finite compactness fails in the finite, right? Now, in the time left, let me show some more important theorems in model theory fail in the finite. I'm not going to even mention what the main theorem is. Make sure I got all the. Yeah. Okay. So connectivity is not definable. 4. The wet definability theorem says that relation I mean this there are a few theorems that deserve to be called beautiful, and this is one of those theorems, and it's way out of our course for me to take up, but I will just tell you that it fails, and in the process you will see what the theorem is about, right? So basically, when I consider over finite models, there is a first order sentence that which defines a unary predicate P implicitly but not explicitly. So what is this explicit, implicit? Implicit. So we have already said what is explicitly definable, right? When is a relation R definable? Well, in a structure, if you like, in a structure, when is a relation R definable? If it's an n-ary relation, there is a formula with n free variables such that the set of all n tuples over which makes alpha true is exactly the relation R. This is what I said as R is definable. That's actually what is called explicitly definable. Beth considers, out of the blue, it's a really, yeah. So an idea of implicit definability, where what you do is, well, consider if you take a vocabulary with some relation symbol R, right? Now consider the language without R, right? If I consider the language without R and consider any structure over that, right? Now, maybe I should write the definition. So, yeah. So, the structure A, actually, typically we say theory T defines P implicitly if for all structures A at most one n-ary relation R over the domain of the structure A such that yeah, it's a complicated notion, and as I said to even, so what Beth is trying to say is that knock off that relation symbol from your language, right? Now consider all structures that are definable, right? Now there is at most one extension. You take any such structure A, right? There is at most one relation that you can define. You can also say exactly one relation that makes all the sentences in T true. So that means the theory T implicitly defines that relation, right? Because syntactically there is for all this thing. So this is no occurrence of T, right? So that is the idea. So you may have an infinite set of sentences, right? Implicitly defining a relation like this. Yeah. This is there is a single formula. Yeah. Explicitly defined. And as I said, the theorem, Betz theorem, is again one of the founding theorems of model theory. It says that first order logic has this considered over arbitrary structures, has this property that even if we have infinitely many sentences together implicitly defining a relation, it can actually be, you can get a single formula that describes it. That's what it says. That's why I said it's a complicated theorem. But and what is interesting is that it fails in the finite. Why is that? Well, let's get paisa vasool from our little uh, parity. Yeah, again I'm going to use parity. So the sentence that I write is as usual as done as a linear order, and I write there exists x px for all y x less than or equal to y. So p is true of the maximal element. That is the idea. So the implicit relation P that I am talking about is a unary relation, and it talks about the maximal element. And then for all x for all y, successor y is a successor of x implies you can see what's going on.
So John, is that an animal element or the max?
I put minimal. It doesn't matter, right? No, it doesn't matter here, as you will see, because of the equivalence that I'm putting here. You're right. It's a minimal element. But now I'm saying every element P holds, the next element P will not hold. So what I'm talking about is parity again, right? So that's why it doesn't matter. It can be even or odd, whichever. So now, for every finite linear order, right, Px holds x is an even element, right? So if you had, so let's call this phi. So phi is the theory, right? The theory T that I'm talking about is this singleton set, phi, right? So if for some theta, if Betz theorem were to hold, there would be some particular sentence, some formula theta with one free variable that will explicitly define it, right? For some theta, then we have a contradiction. Because theta would define evenness, and I know that theta is not, evenness is not definable. Right? So it's a completely trivial kind of argument compared to what. So Betz definability theorem fails. Next is another very important theorem of model theory. Craig interpolation theorem fails in the finite. And that's another very, very nice theorem. It says that if in general you have got alpha implies beta as a validity, then for some gamma such that vocabulary of gamma is contained in vocabulary of alpha, intersection vocabulary of beta, you have This is called an interpolant. Okay. So it says if alpha implies beta is valid, then you can restrict yourself to the common vocabulary of alpha and beta, right? Alpha talks about some p's and q's, beta talks about q and r. You can factor the implication through, right? So it's really nice. So from alpha you can get gamma, and gamma you can get beta. And of course, Craig interpolation theorem actually says this with single turnstile. So you can actually derive these as theorems. So you can do in proof theory, it's all done through proof theory. But anyway, what is interesting for us is that Craig interpolation theorem fails. And let's see why. Okay. So let's fix some linear order. Then there is a, so fix your language of order that you've got. There is an L union. So I'll just assume that there is a constant C available to me. Yeah. L union P sentence phi 1 and an L union Q sentence phi 2 such that phi 1 implies phi 2, but no L sentence theta such that and you know where this is coming. No L sentence theta to say something is not definable. What is not definable? Well, our friend parity, right? So this is how it. So to show that Craig interpolation theorem fails, I have to show I take L, extend it with some P, and with Q. So now I have phi 1 implies phi 2 is a validity. If Craig interpolation theorem were to hold, I'll have something in the common vocabulary, so it'll have to be an L sentence, right? Phi 1 implies theta and theta implies phi 2. This is what I would have to get, and that's not possible because theta will define parity, and that is not definable. This is the idea, and the kind of mechanics is pretty similar to what we've been doing. Okay. So, oh, I'm sorry, I erased that phi. So let me write phi prime as phi that we had earlier, where you remember P that I had defined, right? That Px and what I had talked about. So now I have phi prime, which is wherever P comes, I replace it by Q. So it's going to play the same role, right? P is going to talk about parity and Q is also going to talk about parity, except that it talks about a particular element. So phi 1 says phi and P of C. The constant C is interpreted at an even position. That's what it says. And phi 2 says phi prime implies Q of C. So clearly, phi 1 implies phi 2, but because phi and pi C implies phi with P replaced by Q implies phi C. So that's not a problem. But if theta is an L sentence of this kind, then such a theta will give me theta is a sentence, right? Now I have turned it into this is also without free variables, and this defines P explicitly, which is not possible. We just saw that can't be true. So I'm just, you build one on top of another, right? Typically, like what we do. So Craig interpolation theorem fails, and I'll shut up with one more. Give me a couple of minutes extra to prove this. So the Wojtarski theorem fails in. And this is that a formula, actually, sentence. A formula let me write it for sentences. A sentence is preserved by submodels if and only if it is equivalent to a universal sentence. And this is actually a very simple theorem. The one direction is obvious. If A is a substructure of B, right? If A is a substructure of B and B satisfies for all x alpha, that's easy to see, right? If B satisfies for all x alpha, right, whatever elements that I pick, alpha is true, I am looking at a subset, right? It's certainly true over the larger one. So universal sentences, universal formulas are preserved by submodels. Existential formulas are preserved upward. If I find a witness, it's going to continue to be a witness. So this is easy. But Wojtarski theorem says the other way also is true. If your property is preserved under submodels at all, then it is actually, I can write a universal formula equivalent to it. That's not an easy theorem to prove. Not very difficult either. It's not like bad definability or anything. But it's a very nice theorem. And preservation theorems are very, very important for model theory. So this is for universal sentences. Then there is a theorem which says that a universal existential sentence is true if and only if it is preserved, if and only if something is preserved under union of chains, if and only if it's equivalent to a universal in the existential sentence. So there are nice theorems. Almost all these theorems fail in when you apply yourself to finite structures. And this is the motivation for finite model theory, why you take finite model theory seriously and study. Pretty much all model theory has to be reworked. And this is so for this, the structure that you consider, which is very easy to write, so let me not write the thing. Basically, you take a linear order and make sure that the last, like you say L is a linear order, every element y is a successor of x is if y equals x plus 1, or x is the last element and y is the first element, right? So what is the advantage of a structure like this? Well, take any substructure. Substructure means it also has to be a linear order, right? Then it has to be itself, right? Why? Because I can't have something that is missing, right? So the moment it satisfies that my formula for all x there exists y such that successor of x, right? Once it satisfies that, right, it has to be the same structure. Therefore, so to show that Wojtarski theorem fails, I have to consider, right, a property that is preserved under submodels but not equivalent to any universal sentence, right? So that's what I need to show. So I take a particular structure of this kind, this is A, and so the formulas, give me just 1 minute more and I will write it all. Yeah. So I'll write, so C says less than is a linear order and 0 is the least. Successor of xy, so y equals successor of x, or x equals last and y equal to 0. And then I write phi equals c, and for all x there exists y implies there exists x px. Okay. Now we can show that it's preserved under substructures, but I'll also show that it is not equivalent to any universal formula. Suppose phi is equivalent to suppose you have this equivalent to for all x1 to xn some theta x1 to xn. This is quantifier free. Yeah. Now what I do is to take two structures A and B, right? A is 1 to n plus 2 less than successor that I have to, S I have to interpret, and then this is the interpretation for P. There is no element satisfying P, right? Remember, this says that if for all x, y there exists, so this implies there exists x, p, x, right? So in one of them, P is false, and A satisfies C and for all x there exists y. Remember, A is that structure that I just wrote. X, y. Therefore, A does not satisfy phi. So therefore, for some A1 to An belonging to 1 to n plus 2, A bar does not satisfy theta, right? We have assumed that this is equivalent to this. So for some choice of n elements, theta is not true. Now I consider B to be the same structure 1 to n plus 2 with the same interpretation otherwise, but now I make P true in some D where D is different from, that's why I have two extra elements, right? So I make P true in D. Now B does not satisfy phi. Remember that phi is preserved under submodels, right? And therefore here it is not satisfied. But we can check that B satisfies C and it also satisfies there exists x px, right? So therefore B satisfies phi, and that's a contradiction. Yeah. So again, we are just using the fact that the particular property that we were talking about is something that you cannot define. Okay. Sorry, I took a little longer. So we are not going to do, this is all just a advertisement for finite model theory and descriptive complexity, and for anybody who wants to take up and follow. But there's a beautiful paper by Yuri Gurevich from 1984, I think, where he called it the challenge of computer science for logic, where he shows, so this are all from different places. I think the first one that I mentioned, parity is not definable over linear orders, and using that for connectivity comes from Gurevich. This I think is Hayek. This is Tate. So different people have proved the failure of many of these, but it's clear that pretty much except for the shining exception of Benjamin Rossmann, who finally in 2005 showed that the homomorphism preservation theorem holds for over finite structures as well. In general, pretty much any model theory, if you take a theorem of model theory, it fails in the finite. Compactness, of course, fails. And all the Lowenheim's column theorem fails. So this is the motivation for doing finite model theory, and which really is the gift of theoretical computer science to logic, I must say. right? Because much of it came up. The origin is from Fagin's theorem, where he showed in 1975 that existential second order logic exactly captures the class NP. And so this finite model theory and descriptive complexity kind of came up together, and now, of course, I mean, you don't, all of these is one area, but EF games is a very important tool. I mentioned also locality last time. In fact, from EF games you can also show a kind of very powerful what is called a sphere theorem for first order logic over finite structures, where you can show that for any element you have to take only a sphere of radius 3 power n, and all formulas can be described by a normal form based on that. So EF games is a kind of entry into that, and that's why I wanted to do it. So I'm not going to do much more of this, but if there is interest later on, I can pick up something. Okay, yeah, sorry I took much longer today. Okay, thank you.